All right, let's get started. Welcome, everyone. This is the last session for LCTS today, the session topic is storage. We have 3 papers here talking about storage or in-memory store, and we are going to have 2 in-person talks followed by 1 virtual talk. And the first talk is going to be given by Jun Lee. He is a PhD candidate at Southwest University, China, and he is now a visiting student at National Institute of Informatics in Japan. Let's welcome the speaker.
Okay, hello everyone. I'm Jun Lee from Southwest University, China and National Institute of Informatics, Japan. I'm delighted to present our work report today. And this presentation has 4 parts. Let's start with the introduction and the motivation part. So SSDs are well used in PC, data center, and high-performance platforms, and are emerging to be the dominant storage device. In order to cut down the unit price of SSD, the bit density has developed from the SLC to TLC, QLC. Which contribute to the well-spread use of SSDs. However, the high-density SSD is easier to have errors and even to lose the data, so reliability of high-density SSD become a major issue in this context. To address this issue, RAID, a redundant area of independent disk, are used in SSD to remove the single point of failure for better reliability. Let us have an example. The data chunk on the different SSD channel can form a data strap. This example only have 2 data chunks for simple presentation. In order to avoid losing the data on either of channels, RAID 5 generates the parity chunk by XORing the data chunk in the same strap. Consequently, either of channel is unavailable, the remainder chunk can be used to restore the lost data. But there is a bad phenomenon in this case. Consider the case of D0 or DO is updated. Because SSD do not support in-place update, so we need to first invalidate the old DO and then find a new place to store the in the same channel to store the new content of DO. After that, we can recompute the parity chunk and save it in a new place on the channel 2. So we can find we have 2 write operations to satisfy only 1 read request, which must damage the average and tail latency of I/O requests. Besides, the software overhead of read controller becomes a major component in the latency of read requests in SSD, which has been verified in the previous work. Thus, the previous works, CR5M and the Fusion read introduce a replication functionality in the read SSD to mitigate such software and XOR overhead during the update write. Let's return to the example. When the DO update, instead of write the new content, recompute the parity chunk, the 2 replica RO and RO prime will be distributed in the different channel. These 2 data are mirror data. Thus, it can cut down the software and the XOR overhead when DO updates. However, the old chunk DO becomes semi-invalid. So why call it as a semi-invalid? The DO is now up to date, but it must be kept to protect the D1 in the original strap. That is to say, this semi-invalid data should also be considered as the valid chunks, although they are out to date. What is the next effect caused by the semi-invalidator. Next, I will introduce the garbage collection in the SSDs. This is an example of garbage collection. SSD do not support in-place update, and read unit of SSD is page where the erased unit is block. So when the block I is selected as the garbage collection candidates block, it must first copy the validator to the other free page. In this example, the PO should be moved to the free page in the block J. It first read to the SSD controller and then write to the block J. In the context of semi-invalidator, and they also should be moved during garbage collection. For example, the P1 in this example. Finally, the block can be erased for claiming the free page. And in this example, the semi-invalidator caused more migration overhead during the garbage collection. Furthermore, we do the preliminary study on the page move by using the previous replication-enabled method CL5M and fusion read. And this figure clearly shows these two methods yet more page move by more than about 5 times and 2.5 times in construct to conventional read 5. That is to say, the increased page move operation delays the processing of the regular application I/O requests. So we have done work to address this issue. Then let me show you the design specification of this work. Our basic idea is only replicating the most frequently written chunks for maximizing the benefit of replication with software and XOR overhead reduction, and also minimizing the cost of the semi-validator. We propose the rep rate, and this method is first utilize the proposed model to distinguish the request to the two parts, and then the replicated pair will be combined with the original strap to form the new strap. To implement our proposal, two issues need to be addressed. The first issue is why and how to replicate the most frequently written chunks. And second issue is how to reduce the overhead during the garbage collection. And in the following, I will talk about our proposal to deal with these two issues one by one. The first issue is why and how to replicate the frequently read chunks. We propose the model-based replication method, and it only replicates the read chunk whose update number are over than the FI star. And to satisfy this, we construct the following formula. And the left of the formula means the benefit of replicating the written chunk, and the right side represents the cost of replicate data chunk. And in this formula, the Fi means the read access frequency of the block I. The T XOR and T soft means the time of XOR computing and the software overhead. And the TR bar means the average saved time for reading a replica. And the TGC, reorganization bar means the average time of each GC processing and the strap reorganization. And the TXOR, T software is set based on the real test, and the following TR, TGC, and T reorganization are estimated based on the last time window. if the benefit is over than the cost, we can get the equation of the Fi star, that is the threshold of replicating the chunks. And furthermore, to set a more suitable time window, we introduce the T star, and it's as T divided by the Fi star. And the second issue is how to reduce the overhead during garbage collection. We propose the strap organization method, and it totally has 3 cases. The first case starts from the semi-valid chunk. In this example, the GC garbage collection candidate block is selected. The DO is a semi-valid data and need to be moved to the free page in the other block. So the first step is the valid page move, and then it searches the replicate chunks in the same channel to semi-invalid chunk D1. And now the R1 prime and D1 is matched. Then the new parity should be rewritten. It recomputes the parity and write the new one in the original channel to the parity. Now, after that, the replicate chunk R1 and D1, semi-invalid chunk D1 can be set as the real invalid, and this page can be reclaimed during the garbage collection. And the DO can be set as a valid from the semi-valid. Finally, the new strap completes the reorganization. And if the garbage collection candidate block only has the invalid page, it can be erased. And the third case starts from the replicate chunk is similar as the first case. And the third case moves the left chunk. Due to the time limit, we do not introduce them in this talk, and more implemented detail can be found in the paper. We have carried out certain tests to evaluate our proposed approach. We implement our proposal in the SSD SIM simulator, and the setting is as follows. Totally 9 block I/O workloads from the MSR trace are used to evaluate the proposed method, and detailed information is shown in the table. There are 4 evaluate methods. First is baseline rate 5, and following is 2 relative work, CR5M and fusion rate. These 2 methods both only replicate the small size write request. And the final is our proposed rep rate. In the evaluation results, we totally show the 3 main results. First is the I/O response time. In this figure, the y-axis represents the normalized I/O response time, and the lower the better. Because our proposed rep rate can improve the benefits of making replication and reduce the page move overhead of garbage collection, our proposal can reduce the I/O response time by about 28% and 60% on the average construct to the 2 related work. After showing the I/O response time, the tail latency, which represents the worst case of I/O, is also another concerned aspect. And in this result, we can also find the proposed method replicate rate can reduce the tail latency by about 21% and about 8% on average in contrast to the baseline rate 5 and the related work fusion rate. And finally, I will show the page move results. In this figure, our proposed method rep rate can raise the page move number during the garbage collection by about 58% and about 31% on average in construct to the 2 related work CR5M and the fusion rate. And finally, let me have a brief summary on this work. We have proposed an integrated data replication method and a garbage collection method for the RAID-enabled SSD. We first proposed a model-based data replication method, and then proposed a strap reorganization method for garbage collection. And the experiment results verify the effectiveness of our proposed method. Thank you for your time. Please have any question?
All right, any question from audience? Can you comment on the impact on your technique's impact on the SSD aging?
Oh, okay. Let's return to the motivation. The related work, two related work, both enable the replication in the SSD. It's yet more the page mode and the erase. And that means the endurance of the SSD to satisfy the better I/O performance. And our proposal is focused on this replication-enabled method to reduce the impacts of the endurance. But it cannot, in the aspect of the endurance, it cannot be better than the baseline RAID 5. It can better than the related work. Yeah.
Thank the speaker.